What is going on, Year 12s? Welcome to exercise 11.4, network flow problems, which is our second last topic or exercise of the year. So, what are network flows and the key terminology? When we talk about network flows, you got to think about water going through water pipes, all right? Or moving people on a road or a railroad network. So like for speed. Or liters of water. Flow capacity and maximum flow. There's some key terminology we need to know. The first vertex or the start is what we call the source. Where the network ends is going to be the final vertex. That's called the sink. The inflow capacity is a total flow entering a vertex, whereas the outflow capacity is a total volume or kilometers leaving a vertex. The maximum flow through a vertex is the smaller of either the inflow or the outflow. Let's take a look at example 1 to put everything into context. Right, so we've got our network on the right. Just so we know, the source is our starting point. And then the sink is our finishing point. And so when we talk about this graph, the directed graph shows the flow capacities in liters per minute. It's important that we include the unit in the answer. It asks us to determine the capacity of vertex A. All right, vertex A, we've only got the one vertex. Just for the sake of the exercise, I guess, to keep it simple. But if we look at the inflow, all right, the inflow is going to be all the edges that flow immediately to A, okay, but not beyond any vertex. So the 150 and 350, that is not included. And look at me, I almost missed the middle. Look at this sneaky one. Right down the gut, 200 there. So what you do is to calculate the inflow, you would go and add up 200 plus 200 plus 250, which is going to get us, what's that, 200, 200, 400, 650. And this is 650 liters per minute. Pretty large pipes that flow through to vertex A. Could be a city, could be just a little water station point, whatever it might be, doesn't state. Now, the outflow capacity of vertex A is all the water that's leaving vertex A. So here we've got 3 edges. We've got 150, 300, and then 100. Okay, once it hits a vertex, it stops, so we don't add 350 and 250. So let's keep the highlighting trend. So 150, 300, 100 is what we need to add. 150 plus 300 plus 100. That's a bit squiggly. Is going to get us 550 liters per minute. Now, what we do for the last one is the maximum flow out of vertex A. Don't let it trick you. Just think of the maximum is going to be the minimum. Confused? Yeah, so it's going to be the smaller number out of inflow and the outflow that we calculated. So it's going to be, hang on. So it's going to be the smallest because that is, I guess, the maximum output this little watering station can produce. Okay, there's no good that let's say the inflow is 700 or 10,000 liters, but if the outflow capacity is only 10 liters per minute, well, then that's constricted. Everything else is like a big bottleneck just waiting for it to filter through. So that's why the maximum flow is a smaller number, because that's the maximum it can produce, if you think of it that way, in liters per minute in our context here. All right, so the maximum flow, the smaller between the two, 550 liters per minute. So that got me confused too for a sec. But no, it is definitely the smaller of the two. Okay, so if inflow happened to be 500 liters, then you would say the maximum flow is 500 liters per minute compared to the 550. All right, the capacity cut. This is a cut through a network that must stop all flow from the start to the finish. And so ignoring everything that's written above, let's just take a look at the diagrams because I feel like this is going to be quicker. What you notice is we have on the left some valid cuts. On the right diagram, we have some invalid cuts. And what you need to think of is, does the line that cuts through the network stop all water flow from the source? The reason why cut 1 is a valid cut is because this point here, and this point here would stop all water flow if we were to just chop it and put a dam there. If we were to cut instead of this first point at the 100 between B and E, C and E, and then A and D, that would also stop the water flow because the arrow tells us which way the water's flowing. All right, now the reason why the network on the right isn't a valid cut is because the water can still flow from A through to D all the way to the sink. Okay, so that's why this cut actually doesn't do anything. Okay, whereas the other ones on the left, they'll stop all water flow. Now, the capacity of the cut. What this is talking about is how many, are we talking about liters here? Kiloliters? Well, just imagine we're talking about liters. Capacity of the cut just talks about how many liters of water we are stopping with the cut. With the cut. Okay, so what we have here is a network. We've got our source. So this is where it starts. Just make note. And this is where it finishes. It's really, really important that you recognize which point in the cut stops the water flow. For example, does this cut here on the 10 liter edge, is that going to stop the water flow? If you answered yes, you are correct. Okay, imagine there's water flowing. All of a sudden, it hits the point in the cut where we've barricaded it. The water stops flowing. And so when we look down here, where the cut is on the 7 liter edge, is this a cut? No, it's not, because we don't actually have any water that's traveling down because the source has already been cut. Okay, so not a valid cut. So valid cut. This point here, the water's already been stopped by the previous cut, not valid cut. And so this leads us to the cut on the 6, the 6 liter edge. If you think about it, the water source is still flowing. If we hit that cut right there, that is actually a valid cut that will stop the water from the source. So valid cut, blue being the water. So water. Okay, the squiggly lines, no water. All right, so everything beyond the valid cut no longer flows any water. So this point here on the 4, this is basically not valid cut. All right, because the water flow has already been stopped by the 6, because it travels this way, up here, and then through to the sink. Okay, so the 2 outside cuts has already constricted the water, and we've got actually one more, don't we? We've got one more point here. What you notice is, yes, the water got cut at the 6, but it has a change of direction and take the 5, and it can travel to this point here on the, I guess, on the 2-liter edge. Okay, so this here is a valid cut. All right, so what's important to know is anytime the cut actually stops the water, that is what we deem a valid cut. All right, and it's important to distinguish between which ones are valid and which ones aren't. Or, yeah. So then we know which ones to add. All right, so it's good to draw, like highlight in blue as well, to track where the water flow is going, so you don't miss any points. And so what we then do is, once we've figured out where our valid cuts are, we want to highlight the number as well. Okay, so we want to highlight the 10, okay, the 2, and the 6. All right, so capacity of the cut is going to be all the valid cuts added together, which is going to equal 10 plus 2 plus 6, which is going to be 18. All right, and it's sort of a methodical process. Often people get this point wrong. They'll see, oh, it's traveling as 5. No, it's wherever the cut edge is, or wherever the cut crisscrosses the edge, that's the number you take. So whilst it looks like it's 5, it's actually on the 2 edge. So that's why you take the 2. Hopefully that makes sense. You just got to like visualize water flowing through the arrows from the source to the sink, and that should help you with capacity of the cut. Alrighty. Lastly, maximum flow and minimum cut. This actually takes a lot of trial and error, and it takes a little while. There's no real other quicker way to do it. So the maximum flow from source to sink can be determined by finding the cut that produces a minimum value, which is essentially what we were doing here. Okay. To determine the maximum flow for a network, identify cuts through the network. So we actually got to make sure that the cut actually fully stops all the water, and then find the capacity of each cut, meaning we have to add like what we did up here. And then maximum flow equals capacity of the minimum cut. So whatever we added, for example, the capacity here is 18. Do we know if it's the minimum cut? I don't know. We'll have to try and error. But down here, they want us to find the minimum cut. And so what we need to do is we need to just draw lines through the network by trial and error. So this is complete trial and error. But obviously you can make educated guesses. So for example, if I were to cut here, this green line, or let's make it yellow. If I were to just cut that, what we would get is a situation where we've got 26 plus 17 plus 12. 26 plus 17, 33, 43 plus 12, 45, 55. And straight away, we can see that's definitely not it. We can definitely get lower than 55 if we were to just even change our cut to something like this. So if we called this one, the green cut. The green cut is going to be 20 plus 8 plus 11, which is going to be 39, 28, 39. And you actually got to make sure it's a cut. Like if you just go, oh, look, I got 19, that ain't it, because water's flowing right past it. Okay, so it's got to constrict every single source, water source, basically. Anything else? Maybe I don't want to cut 26, because anytime we cut 26, we can cut 20, if that makes sense. Like you don't want to cut the longer one if you can see constricting 20 is going to be immediately better. What if we cut 28 and then we have to go through the 8 and 12? What's that? 28. Call this cyan. 20 plus 8 plus 8 plus 12. That's not going to win. Or is it? 20, 40, 48. Damn it. No. All right, let's see if we can beat 39. Again, cuts like this, they don't count because water flows would go through the middle and lie at the top. It's got to constrict all water sources. 11, 19, nah. Yeah, so our winner is the green line. Okay, so this is going to be the maximum flow. And then the rationale is that looks like a W. Maximum flow because the green cut is the minimum cut. Oh. Minimum cut. All right, so every time you see maximum flow for a question, you got to think, all right, what's the smallest cut? What's the minimum cut? And that's all for exercise 11.4. Let me know if you have any questions. Thanks, everyone.